So here the question is to count negative numbers in a sorted matrix. So the question is given m into n matrix grid which is sorted in non-increasing order both row wise and column wise. Return the number of negative numbers in the grid. So there are 2 3 points. The first one is that the grid is sorted in non-increasing order, which means it is sorted in descending order, and it is sorted row wise as well as column wise, and we are supposed to return the number of negative numbers in the grid. Let us take an example to understand this thing. This is our example. Over here we can see that the grid is sorted in descending order, so the first and that is column wise as well as row wise. So let us see row wise first. This is 4, this is 3, this is 2, this is minus 1. So 4 is greater than 3, then it is greater than 2, and it is greater than minus 1. Looking column wise as well, the grid is sorted. 4 is greater than 3, 3 is greater than 1, 1 is greater than minus 1. So if such an order of sorting is done, then we are almost sure and we are completely sure that the negative numbers will always lie in the lower diagonal of the matrix, because these are the least numbers, and in descending orders in descending order the least number will always come at the end. So they will always lie in the rows end, that is the right part. If row starts from the left and goes till the right, so these number will always lie in the rightmost part, because the matrix is sorted in the row wise sorted manner. Similarly, they will always be found in the downside of the column, because matrix is also sorted in the column wise order. So what we are supposed to look at the lower diagonal of the matrix to find the number of negative numbers in this particular matrix or any other matrix of this kind. So this is our question. Now let's come to the solution part. There are two kinds of solutions. One is brute force. This is the first kind of solution. The second kind of solution is optimized. I'll just explain the brute force code and then I'll move quickly to the optimized code, because brute force is senseless over here. Just for the sake of explanation, I'm giving you the solution. In brute force, we will just apply two for loops. I is equal to 0, I is less than rows, I plus plus. Over here, we will apply one more for loop. J is equal to 0, J is less than columns, J plus plus, and inside we will just add 1 to the count element. We will initialize count with 0 and we will return the count. It will work like this. First it will go to this row. It will see if it is less than 0. If grid of I j is less than 0, no it is not, then it will go to 3. It is not. It will go to 2. It is not. It will go to minus 1. It is. So it will increase count by 1. Then it will go to the row number 1. Over here again it will check, this is not, this is not, this is not, but this is yes. So again it will increment 1. Then it will go to this row. This is not, this is yes, this is yes, this is yes. So it will add 3 to it. Then here yes, 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 yes. Finally count will get the value of 9, which will be the answer. This was the brute force code, which is hardly required over here, but this code will fail eventually, because if we look at it, the no, it won't fail, but it is not something that they are asking for. It they are asking for this kind of solution, or they are asking for optimized solution. So brute force is not required over here. Now I'm coming to the optimized solution. Optimized solution. Now For optimized solution, we have to leverage the other things that are given in this question. The most profound thing given over here is sorted. The array is sorted in non-increasing order. That is, it is sorted in descending order. So if the array is sorted, we just have to apply one single algorithm, because one single algorithm that works on sorted system is binary search. So we have to just blindly apply binary search on this question. But binary search cannot be applied blindly, because it is not just given over here that you can apply this and the constraints or the conditions are similar. So we just use some improvisation to apply it appropriately. Improvisations. Just ignore the spellings because I am not good at it. Now if we apply binary search on it, we get the time complexity reduced. The brute force time complexity was big O of n square. The optimized binary search time complexity would be big O of n log n. And mathematically, as well as practically, mathematically, big O of n log n is fairly faster than big O of n square. So this solution becomes optimized. And this becomes brute. Now let us see how do we apply binary search on it. Let us see a one dimensional example of this sorted array in decreasing order. So let us say 5 is the biggest element, then 4, then 3, then minus 1, then minus 2, then minus 3. Obviously, it is sorted in decreasing order because this is larger than this, larger than this, larger than this, larger than this, larger than this. We have to find the number of negative elements in this array. Number of negative elements visibly in this array are 3, which is minus 1, minus 2, minus 3. So 3 elements are negative in this array. Now using binary search, we can find this answer as 3. What we do is we find the middle element in binary search. The middle element in this binary, let us say the first index is left, which is 0, and the last index is right, which is 0, 1, 2, 3, 4, 5. So the last index is 5. We find the middle element. Middle element is equal to right plus left by 2. So right is 5 plus 0 by 2, which is 2.5. Since it is integer data type, so we will take the floor value, which is 2. So middle element will be at index 2. This is mid. Now we check. Let us name this array as n. So now we check if n of mid is less than 0. Well, it is 3 and it is not less than 0. Since it is sorted in decreasing order, so every element ahead of 3, that is every element after 3, will be lesser than 3, and every element to the right of 3 will be larger than 3. So if there is an element which is positive, so on which side of this element we will find negative elements? Obviously we will find negative elements on the right side, because it is sorted in decreasing order. So every element on the right of it will be smaller than this. So obviously there are fair chances that we will find negative elements on the right of it. And there are sure chances that we will not find a single negative element on the left of it, because every element is greater than 3. So we just push L to mid plus 1. So L is equal to mid plus 1. So L, from instead of being 0, L now comes over here at this position, which is third index. Let me erase it. Now L comes at position 3 and R comes at position 5. So earlier we had the window of checking this long, that is from index 0 to 5. Now the window reduces to this long, that is from index 3 to index 5. So obviously we reduce the searches to half. This is the power of binary search. That we just check a single value and determine logically if we have to move ahead or we have to move behind. We don't have to check every single element by picking it up. So by binary search, we just reduce the time complexity to very, 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 very short duration. Okay. Now we again calculate mid. Mid is equal to r plus l by 2. So mid is equal to 3 plus 5 by 2, which is 4. So mid comes at this index. Now again, if nums of mid is less than 0, well, it is minus 2 this time. It is less than 0. Yes, it is less than 0. Now we have found our first negative element over here. But what are the conclusions logically to be made over here? Well, the conclusions are that every element to the right of minus 2 will be negative because it will be less than minus 2 due to the sorting reasons. So every element less than minus 2 will be negative because minus 2 itself is negative. But we do not know if element which is greater than minus 2 will be negative or not because minus 1 is greater than minus 2 and minus 1 is negative. But 1 is also greater than minus 2, but 1 is not negative. So we have surety on this side that every other element will be negative. But on this side, we have no surety. So we can just safely and blindly assume that this side will be negative. So what we do is we just reject this side and come logically to this side. Why do we do this? We do this because we are sure that the right side is already negative. Just like we eliminated this side because we were sure. Now we are eliminating this side because we are sure. So we are logically eliminating sides to reduce the number of iterations. So now R comes at this side, that is mid minus 1. We do not bring left and R to mid because we are already checking that index. So we just either bring mid plus 1 or we bring mid minus 1. So R is equal to mid minus 1. Okay. So R comes at this index 3. Incidentally, left and right are both coinciding on this third index. So let us see, we calculate mid again. Mm, Mid is equal to r plus l by 2. R is 3, l is 3. 3 plus 3 by 2 is 3 itself. So mid is 3. We again check n of mid. Is it less than 0? Well, minus 1 is less than 0, definitely. So we again form some conclusions and go ahead with it. Well, the conclusions are that every element to the right of this index will be negative for sure. So we eliminate this part. But we still do not know every element on the left of it will be negative or not. So we again bring right to mid minus 1. So R is equal to mid minus 1. Mid O in this case was 3. So 3 minus 1. R is equal to 2. Now whenever we run binary search, we have a condition in the while loop. L is less than R. Now L is 3 and R is 2, so they won't run and the loop will exit. This is the beauty of binary search, that whenever we find the answer, that is we find the least negative index. See, 1 was the only point from where the numbers started becoming negative. So we already found the least index of the negative numbers. The index of the negative numbers were 3, 4 and 5. 3 for minus 1, 4 for minus 2 and 5 for minus 3. The least of them was 3 because everything started changing from this particular index, third index. Before that, everything was positive. Negativity started from this third index. So, whenever we find the least index or whenever we find the point of inflection, the loop itself exists due to this condition and the loop will not run. This was the beauty of binary search. So, we eventually find the least negative index L and I at mid, and this is So we found the least negative index at mid. So ln I is equal to 3. Now we just have to do a little bit of calculation and get our answer. The calculations that we are supposed to do are, we name a variable count, and we say that um, n dot size minus ln I. Well, what is the size? The size is 6. 6 minus 3 is equal to 3. So the count of negative numbers is 3. Well, this was the entire size, which was 6. And this was the negative part. If we remove the negative part from the entire part, what we are left with? The positive part. And vice versa. If we remove the positive part from the whole part, what we are left with? The negative part. And we were supposed to find the length of negative part. So this least negative index signifies the positive part, the terminal of positive part, because this was the point of inflection, third index, from where the thing started getting negative. So we just removed this thing from the entire thing, and what we were left with was the negative part. So this was the game, and I guess you understood the entire concept. Now, coming to the grid part, how do we solve it in the two-dimensional array part? Well, that's very basic. We start from row 0. We apply binary search on this particular row. Then we go and we find the count value of count. Then we go to this row. We apply binary search on this row. We find the negative number of negative elements in this row. We add it to the count. Then we go to this row. We find the number of negative elements in this row, which is this. We add it to the count, and then we go to this row. And logically, we just add the number of negative elements in each row. So we are having n rows, for example. So we are traversing n rows. And in each row, in order to find the number of negative elements, we are applying log m, time complexity, where m is number of columns. And when we report it asymptotically, we just say big of n log n, because n and m are similar in size. Now I am showing you the code, the optimized code. You can just take the screenshot of this code. This is the code, and after this I will give you some examples where you can dry run it yourself to get a better understanding.
I am giving you some examples which are also very important, and you can solve those as well using pen and paper so that you can understand the concept well. So the examples over here are, these are the four examples that I have given you. This is a normal one, this is also a normal one, this is a big one, and this is a small one. You just take the screenshot of the code, write it down on a paper, use a pen and a paper, and solve code line by line on each single of this example to get the clarity of the concept. Thank you.